Looking at 8.6, which is the approximation to the binomial distribution. What we want to do in this chapter is actually use that normal distribution, which is a continuous distribution, to approximate the binomial distribution, which is a discrete distribution. The reason that we really want to do this is think about when we had our binomial distribution. Okay, let's go through some properties of the binomial distribution. So for binomial, there were three major things that we really had to remember. The first thing was that in binomial distribution, number one, it's discrete, but that means that there are only finitely many possibilities. Okay, we have a finite number of trials. So we have n trials, and the probability of success in any one of those trials was given by the probability p. So p is the probability of success in any trial. So let's say you had 10 trials, and then for each trial the probability of success in any one of those trials was given by p. We also have to remember that there are only two possibilities, only two outcomes. Okay, so you're going to have your outcome of success and your outcome of failure. So there's only two outcomes, and we call them success and failure. The thing to remember with this, go back to an example. We always looked at throwing a coin, okay? When you toss a coin, you have either heads or tails. And we normally said, okay, a success could be heads and failure would be if you got tails. We also looked at a problem where we rolled a die and you said, okay, if I roll a 5, that would be a success. But if I rolled anything other than a 5, there would be failure. So even though on a die you have more than one outcome, more than one possibility, we just narrowed it down to say, okay, this thing means success, anything else means failure. So there's only two outcomes in this situation. And the third thing to remember is that the trials are independent of one another. So whatever happened in a previous trial, so a previous toss of a coin or a previous roll of a die, does not affect the next one. Okay, it does not affect the next trial. The thing with binomial, as I've said, is it's a discrete distribution. And remember, discrete means that there are a countable number of outcomes. Okay. So if there are a countable number of outcomes, we normally looked at things like rolling a die, where you could have your outcomes are 1, 2, 3, 4, 5, 6. Okay, so there's a countable number of outcomes there. But then when we went over to normal distribution, you had infinitely many outcomes. Okay, you could come up with some infinitesimal decimal that could be a possibility. We looked at time, height, and weight as examples of a continuous distribution. But what we want to do now is to say, okay, for some distributions where we use this binomial distribution, for some of these problems, the issue that you have is that back in the days before they had calculators, when they were looking at the number of successes, so let's say you had, for example, 1,000 trials in some situation. So you were tossing a coin 1,000 times, you were rolling a die 1,000 times. And what they wanted to do was they wanted to figure out the probability, let's say, of having at most, so less than or equal to, 600 successes. So for their binomial distribution, they wanted the probability that x is less than or equal to 600. Now, if you think back to when we did this, all we did was we went to our calculator and we've got this less than or equal to here. So we knew that we could use binomial CDF in our calculators. And all we would have to do is type in number of trials, in this case 1,000. You would type in the value of P, which if you're tossing a coin would be 0.5, would be your probability of success, your probability of getting heads. Or you could then say, okay, well, I've got my N and I've got my P, but then I still need that value, we call it X, where you were looking at the probability that it was less than or equal to some x value. Remember, we always needed less than or equal to the value that you typed into the calculator. So go back and look at this on your calculator to kind of give yourself a refresher on this. But in this case, if we're looking for the probability that x is less than or equal to 600, we know how to type that into a calculator. Way back when, they didn't have a binomial CDF function. They didn't know what to do. It was a formula that you can use when you're trying to figure out the probability that x is equal to something, okay, whatever that number may be. They have a formula for that. There is a formula that uses combinations, and it's not exactly the easiest formula, but we do have a formula where we can figure out in binomial distribution the probability that you have an exact number of successes. It's not a less than or equal to, it's an exact number. So what they used to have to do, if they were trying to figure out the probability that x is less than or equal to 600, they would have to sit there and plug some numbers into this formula and figure out the probability of every single one of these and add them all together. So they looked at having 0 successes, 1 success, 2 successes, etc., all the way up to, in this case, 600. That would take a very, very long time. It's very computationally expensive when you're using a formula like that. So what they said was, well, we've got no other way of calculating this probability that x is less than or equal to 600, the probability that I'm going to have at most 600 successes. What can we do? So what they did was they said, okay, well, we know how the normal distribution works. They have way more information about the normal distribution. So they said, we're going to take our discrete distribution, this binomial distribution, and we are going to approximate it using this continuous normal distribution that we know way more about. So let's come over to our normal distribution. Quick recap on this. I mean, we've only just done this, so I won't go too in depth. If you remember, we looked at our curve, this bell-shaped curve that we've seen many times before. And you'll remember right down the middle is our mean. And we've got a certain standard deviation. So this point here would be the mean plus a standard deviation, and a mean minus the standard deviation. And you can keep going with more standard deviations either side. So when we do normal distribution, we have a mean and we have our standard deviation. So we looked at our standard normal distribution. A standard normal distribution had a mean of 0 and a standard deviation of 1. But that wasn't always the case, as we have just looked at with some of the examples in 8.4. We can have a different mean and a different standard deviation, but what we did was we pulled it back to that standard normal distribution with a mean of 0, standard deviation of 1, and did all of our calculation in that. That's pretty much what we're going to be doing here. So, a couple of things to note. We know that if we've got a binomial distribution, okay, and it's going to have a certain mean and a certain standard deviation, okay, all these distributions, whether discrete or continuous, we're going to have a mean and we're going to have a standard deviation that tells us the spread of data and how spread out it is. If you think back to our binomial distribution, so for binomial, this isn't the case for every distribution, but in binomial we actually had formulas for the mean and standard deviation. So the mean was n times p, so it was the number of trials multiplied by the probability of success. So what our mean was in this situation, it was kind of like our expected number of successes, okay? So it was the number of trials multiplied by the probability of success in any one of those trials. So it tells us how many successes we expect to have. So that was our mean, and the standard deviation was given by this formula, okay? It was np times 1 minus p and then square root, okay? So, quick side note as well. Remember, 1 minus p would be our probability of failure, okay? If p is your probability of success, well, your two outcomes, the probabilities of the two outcomes, success and failure, have to add to 1, okay? There's only 2 outcomes, so the probability that you'd land in either one must be 1, okay? You're guaranteed to either succeed or fail. So 1 minus p would be our probability of failure. So we have our mean and we have our standard deviation. Now, if we're going to be using this normal distribution to approximate our binomial distribution, the obvious thing would be that you have to have the same mean and standard deviation. So before you start out with any of this, when they give you a problem that is in binomial and they say, okay, we want to actually approximate this using the normal distribution. Well, the normal distribution that you approximate it with must have the same mean and standard deviation that we had in our binomial case. Okay, you don't want to approximate one distribution with another when you have a different mean and a different standard deviation. So whenever we do this, always start out by saying that you have to have, so we must have the same mean and standard deviation. When approximating a binomial distribution with a normal distribution. Okay, so you have to make sure that the means match and the standard deviations match. Okay. There's another thing that you have to make sure, and you don't have to worry too much about this, but it's to do with the shape of the curve. Sometimes they will say to you, would the normal approximation, our normal distribution, be a good approximation for our binomial distribution? And there are a couple of properties that means it will be a decent approximation. You must make sure, okay, two things that you would like it to have and two things that you would really like it to have, okay? First thing is that you would like n times p to be greater than or equal to 5, okay? You would like that for at least a reasonable approximation, let's say. You would like that your expected number of successes, so n times p, that's your mean. You would like your expected number of successes to be at least 5, and you would like your expected number of failures to be at least 5. What this does is it makes sure that you've got enough data points, so enough trials, and a high enough probability of success for this thing to actually work out, okay? So you would like the number of successes, and this thing here is the number of trials times the probability of failure. So this is the number of failures, the expected number of failures. You would like both of those to be at least 5 to give you a reasonable approximation. What you would really like is for both of these things to be greater than 10. That would give you a good approximation. Okay, so you'll get a reasonable approximation here. This will give you a reasonable approximation for using the normal distribution to approximate the binomial. This thing here would give you a good approximation, okay? So you really want to aim to have n times p and n times 1 minus p to be greater than 10. That would give you a good approximation for the binomial distribution by using that normal distribution. So that's two things to remember. You have to have the same means for your binomial and your normal distribution and same standard deviations between the two distributions, but you also have to have this property that you would like both the expected number of successes and the expected number of failures to be greater than 10. Okay. The next thing that we want to look at is remembering that the binomial distribution is discrete. Okay, we said that that means that it can only take on a countable number of values. Okay, it's normally 1, 2, 3, 4, 5, 6 or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, you can have from no successes up to however many successes however many trials you've got. You could succeed in every trial, or you could succeed in no trials, or you could succeed in some of them. But you have to make sure that you only have a countable number of outcomes, okay? You're not dealing with decimals here. You're always going to be dealing with whole numbers. When we go over to our normal distribution, so remember we're using our normal distribution to approximate a problem in the binomial distribution. In normal distribution, you can have decimals, okay? So we have to make sure that we remember that. That comes down to something that we're going to look at called continuity correction. Okay. Continuity correction is used when approximating a discrete distribution, like the binomial distribution, with a continuous distribution. Okay, so that is the main time that this thing is used. Okay, is when you are approximating a discrete distribution like the binomial with a continuous distribution like the normal distribution. What we have to do to apply continuity correction, all you have to do is add or subtract 0.5, depending on the problem, to a value before calculating the probability. Okay, we're going to look at some examples of this so you can make sure that you get it the right way. So what it does is this adds or subtracts 0.5 to the value before calculating the probability. Before. Okay. So before calculating the probability. I'll show you first how this works and then we'll do some examples. So let's say, first of all, we'll start with the equality one. Okay, the equality one's pretty easy to remember. It's when you start dealing with greater than or equal to's and less than or equal to's that it gets slightly more complicated. Let's say you have n trials and just a probability of success being p. Okay, it doesn't matter for this, but what we're mainly looking at is that x value. So let's say we're looking at the probability that x is equal to 5. Now, you have to do this before you plug anything into your calculator, okay? They will give you a problem that is in the binomial distribution, okay? So there will just be success and failure. They'll give you n trials and some probability of success, and they will say, what is the probability that I have 5 successes, exactly 5 successes, but I want you to approximate this using the normal distribution. If we do this for the probability that you have exactly 5 successes, what you need to remember is you are using a continuous distribution to approximate a discrete distribution. So at the moment we are in a discrete distribution, but I want to approximate this with something continuous. Now, in a continuous distribution, there are multiple values, multiple decimal values that will round to 5, okay? Anything greater than or equal to 4.5 would round up to 5, and anything up to 5.49 reoccurring would also round to 5. Okay, so what we actually do in this case is we actually say that we're going to have the x must be between these two values. So this thing here is in binomial, and this thing here is in normal distribution. So I am approximating something that is in my discrete distribution with something that is in my continuous distribution, okay? The reason we can go up to 5.5 here is the probability that it's exactly 5.5 in a normal continuous distribution, okay? Remember, you cannot have a probability that it's exactly some value in a continuous distribution. It doesn't work, okay? There is no probability of an exact value in a continuous distribution. We have to have a probability of a range of values. So regardless of whether we take this as up to 5.499999 or we take it up to 5.5, it doesn't make any difference because the probability that it will equal exactly 5.5 doesn't exist. We need that range in there. So we actually take it anywhere between 4.5 up to 5.5. So when you have equality, you take all things that could possibly round to that value, okay? The next thing that we're going to look at, I'm going to start looking at some inequalities here, is if they said, okay, what's the probability that you have at most 5 successes? So that includes 5, okay? If you have at most 5, you can have anything up to 5 successes. So in binomial, okay, this is in binomial right now, and we want to approximate this and write this as something in the normal distribution. So then I can calculate it in the normal distribution. Because remember, they didn't know how to calculate this back in the day, apart from adding together a bunch of values. So we want to know how can we get this into the normal distribution, and then we will calculate it in that normal distribution. So we have the probability that x is less than or equal to 5. Now, what you have to do here, and I will tell you this for all inequalities, always make the set larger, okay? Good thing to remember. And this is the case with all of them. Always make the set larger. Okay, and you'll see what I mean by this when I draw a number line in a second. If you've got the probability that x is less than or equal to 5, okay? Draw yourself a number line. We'll put 0 here, okay, because you can have 0 is the least amount of successes you can have. You can't have less than 0. And 5 is over here, okay? We want the probability that x is less than or equal to 5. So we want the probability that it can equal any of these values here. When you put this into normal distribution to approximate it, we need everything that can round to 5, but we need to make this set larger, okay? So I'm not going to include the values where I'm going to round down. I'm actually going to come up here, okay? Up to 5.5, okay? Anything up to 5.5 still rounds down to 5. So what I actually end up doing is making this set here larger, okay? I make my line longer on the number line, but I'm going to take this into the normal distribution as the probability that x is less than or equal to 5.5. And I'm going to calculate this in the normal distribution, okay? We'll type this into a calculator in a minute and see how it works. But I just want you to see how we're going to get from a binomial distribution into a normal distribution using this continuity correction, okay? Let's say we had the probability, we want to find the probability that x is greater than or equal to 5. So I want the probability that I have at least 5 successes, so 5 or greater, okay? Again, remember, we always want to make the set larger, okay? So this is in binomial distribution right now. I want to get this into normal distribution, okay? So I want to go over into normal distribution and then I can calculate stuff in normal distribution, okay? So again, draw yourself a number line, okay? 0 is the lowest amount of successes you can possibly have. We're looking at the probability of having greater than or equal to 5 successes. So you can go up to however many trials you've got, let's say n trials. Okay. But I want the probability that I have at least 5 successes, okay? Again, we want to make the set larger. So this time, I'm going to come back here to 4.5, okay? Anything 4.5 or greater rounds up to 5, okay? So when I go over into the normal distribution, I want the probability that x is greater than or equal to 4.5. Okay, again, we have made our set larger here, okay? We have this time rounded down and subtracted 0.5, whereas before we rounded up and said, okay, I'm going to use everything up to 5.5, okay? So everything that rounded down to 5, and in this case, it's everything that rounded up to 5. So remember which way round it is, okay? I would always draw a number line so you can see that you are making that set larger, okay? And make sure that you're rounding the right way. The easiest way to do it is to draw a number line. What happens if we have a strict inequality? So let's say I now wanted the probability that x is less than 5. So I know that I want less than 5 successes. This time I'm not including 5. You are still in a binomial distribution at this point, okay? You only go into that normal continuous distribution when you have done continuity correction. Before you have done that, you are still in a discrete distribution. When you're in a discrete distribution, you have a countable number of values. So 0, 1, 2, 3, 4, 5, 6, etc. Okay? So I want the probability that I have less than 5 successes. Okay? Well, if I've got less than 5 successes, that's the same thing as saying that I have less than or equal to 4 successes. Okay? If I've got less than 5 successes, the most amount of successes I can have is 4. So I'm still in binomial at this point, okay? I haven't done any continuity correction. I'm now going to work on this, use continuity correction, and get this thing into normal distribution, okay? Now this time I have a less than or equal to 4. Draw yourself out a number line. 0 is here, 4, 5, etc. You can go all the way up, okay? I want less than or equal to 4 successes. So at the moment, I am looking at this set here, okay? Remember, I want to make the set larger. So because I want to make the set larger, I want all the values this time that will round down to 4, okay? Anything up to 4.5 will round down to 4. Okay, and I have made this set larger. I've made that line longer. So in normal distribution, this would be the probability that x is less than or equal to 4.5. And this is in normal distribution. We have now done our continuity correction. And finally, let's do the probability that x is greater than 5. Okay, we are still in binomial. Okay, this is the problem that you would get in binomial. If I've got greater than 5 successes in a discrete distribution, that means that the smallest amount of successes that I can have is 6. Okay, if I've got greater than 5 successes, this is the same thing as saying I've got greater than or equal to 6 successes. Okay, I'm still in binomial. I haven't done any continuity correction yet. Okay, now coming to our number line. Okay. 0 here, we'll put 6 here. I've got greater than or equal to 6, okay? I want to make my set larger, make my line longer. I'm therefore going to bring it back to 5.5, and anything 5.5 or greater will round to 6. So in normal distribution, this is the probability that x is greater than or equal to 5.5, and that is in normal distribution. So make sure you're happy with that continuity correction, okay, and which way you have to round. But always draw yourself a number line so that you can figure out how to make that set larger and figure out the values that will always round to the number that you want, okay. Okay, so this example says that an advertising agency hired on behalf of Tech Development Office conducted an ad campaign aimed at making alumni aware of their new capital campaign. Upon completion of the new campaign, the agency claimed that 20% of alumni in the state were aware of the new campaign. Okay, so the probability of success, the probability of awareness, P, is going to be 0.2. Okay, they've got a 20% chance. To validate the claim of the agency, the Development Office surveyed 1,000 alumni, okay? So the number of trials, N in this case, is going to be 1,000, and found that 150 were aware of the campaign. Assuming that the ad agency's claim is true, what is the probability that no more than 150 of the alumni in the random sample were aware of the new campaign? Okay, so we want, in this case, the probability that X is less than or equal to 150. Okay, so let's come into here and we want the probability that X is less than or equal to 150. Okay. Now they told us that N, the number of trials, the number of people, was 1,000. And the probability of success, the probability that they were aware of the campaign, was 20%, 0.2. This is in binomial distribution. What we are going to do is we are going to approximate this binomial distribution using the normal distribution. So I want this probability that X is less than or equal to 150. Okay. Draw yourself out a number line. Okay. Zero's down here. Let's say 150 is here. Okay. Remember, the probability that X is less than or equal to 150, I want to go up to the numbers where they round down to 150, okay? Because I want to make my set larger. So this would be 150.5, okay? So this is in binomial here. And using continuity correction, I'm looking for the probability that X is less than or equal to 150.5, okay? So in normal distribution, I know that I want the probability that X is less than or equal to 150.5, okay? Now, the next thing that I need is a mean and a standard deviation, okay? So I know that my mean is N times P, which is 1,000 multiplied by 0.2, which would be 200. And then my standard deviation that I would have is going to be the square root of N times P times 1 minus P. Okay? If you plug in N is 1,000 and P is 0.2, this comes out to the square root of 160, which is approximately 12.6491. So we have a mean and we have a standard deviation. And we have the probability that we are looking for with our normal distribution. So what we are effectively looking at here is a normal distribution where we have a mean of 200, a standard deviation of 12.6491, and we are looking for, in this distribution, the probability that X is at most 150.5. Okay? If you go to your calculator, go to second and distribution, so second and the vars button, okay? And go down to normal CDF. Remember that it asks for our mean, it asks for the standard deviation. It will also ask for a lower and upper bound. Now, we've got the probability that X is less than or equal to 150.5, okay? We have an upper bound, we don't have a lower bound, okay? What you could do is type in a very, very, very large negative number, okay? So you could say that your lower bound is something like -1,000,000 or something. That would work. It would work in your calculator and give you a decent answer. What I'm going to do is link this back to what we have done in 8.3, 8.4, where we've looked at how we can get a normal distribution that doesn't have a mean and standard deviation of 0 and 1, and take it to our standard normal distribution using our Z transformation, which does. So what I'm going to do here, this is in binomial at the top, then we've gone into normal distribution. I'm then going to take my calculation in normal distribution and put it into standard normal distribution. So remember, our formula for that was X minus the mean divided by the standard deviation. So I'd have 150.5 minus the mean divided by the standard deviation. Okay. I now have this thing here is Z is less than or equal to, when you type all of that into a calculator, you get -3.91. Okay. What this is looking at is the probability that you have less than or equal to negative 3.91, but you now have a mean of 0 and a standard deviation of 1. Okay, so you are now in standard normal. So you went from a binomial discrete distribution where you had a mean of 200 and a standard deviation of, you had a mean of 200 and a standard deviation of 12.6491. You then approximated that binomial distribution with a normal distribution that had the same mean and standard deviation as before, but you incorporated that continuity correction into it to get it to a continuous distribution. Then you have stayed within a continuous distribution, so you've stayed within that normal distribution, but what you have done is you've performed a z transformation on it that has taken it from a normal distribution with a mean of 200 and a standard deviation of 12.6491, and you have taken it to the normal distribution, that standard normal distribution that has a mean of 0 and a standard deviation of 1. So what we can now do is, if you go to your calculator, we know that within our standard normal distribution, a lower bound when it's unbounded, okay, when we need a lower bound, we can plug in negative 10. Our upper bound, okay, it has to be less than or equal to negative 3.91, so our upper bound is negative 3.91. We've got a mean now of 0 and a standard deviation of 1. You go ahead and calculate that. You should end up with something around 4.62 times 10 to the negative 5. That is an incredibly small number, okay? This thing actually comes out to approximately 0. If you think about it, that makes sense. What this is looking at is the probability that the z value is less than or equal to negative 3.91. Because we are within standard normal distribution, this is saying, because we've got a standard deviation of 1, you're looking at the probability of being less than or equal to almost 4 standard deviations below the mean. Okay, so if you think about our curve here, okay, if your mean is here, so your mean is now 0, okay, it's asking negative 3.91, if I can draw it down here, you're asking what is the probability that you're all the way down here. Now remember, within 3 standard deviations of the mean, okay, so 3 standard deviations above and below, within that range, so here you should have roughly 99.7% of your data. So it's looking way down one end and saying how much of the data have we got below 3.91 standard deviations below the mean? Pretty much nothing, okay? So the fact that this thing actually comes out to roughly 0 makes sense, okay? So go back to when we did our normal distribution and look at those diagrams again, okay? And this thing comes out to roughly 0. Okay, so now I want to go through this homework problem. And it says, consider the probability that less than 16 out of 148 houses will lose power once a year. Assume that the probability that a given house will lose power once a year is 10%. Okay, so looking at this first of all, okay, we know that we're in binomial right now. Okay, we have a binomial distribution because they can either lose power or not lose power. Okay, they've got success and failure. There's those 2 outcomes. So we know that we're in binomial distribution. We know that our number of trials, n, is the number of houses, 148. And we know that our probability of success, in this case, it's actually the probability that you lose power, is 10%. Okay, so we know that n is 148, p is 0.1, okay, in our binomial distribution. And we want the probability that x is less than 16. So less than 16 of the houses will lose power. Okay. So let's come into here and we want the probability that x is less than 16. Okay. We know that n, the number of houses, is 148. And p, which is our probability of success or the probability of losing power, was 10%, which is 0.1. So from here, Okay, we need to figure out our mean and we need our standard deviation. And then we will need to do our continuity correction to get this from binomial distribution into normal distribution. Okay. First, let's find our mean and our standard deviation. So mean is n times p, which would be 148 times 0.1, which would be 14.8. Okay. So the next thing that we need is we need our standard deviation, which is going to be the square root of n times p times 1 minus p. Okay. So that's going to be the square root of n times p we already know is 14.8. 1 minus p is 0.9. So that comes out to the square root of 13.32. So if we figure out the square root of 13.32, we should get, I'll go to about 4 decimal places. So we'll put 3.6497. Okay, so we have a mean and we have a standard deviation. So at the moment I am in binomial, but I've got a less than. I need a less than or equal to in order to do continuity correction. Okay, so at the moment I am in binomial. Okay, in order to do continuity correction, I either need a less than or equal to or a greater than or equal to. And currently I have a strict inequality, I have a less than. If it's less than 16 successes in binomial distribution, okay, the most amount of successes that I can have is 15. Okay, if it's less than 16, the most you can have is 15. So this thing, still in binomial distribution, can be rewritten as the probability that x is less than or equal to 15. So I'm still in binomial here. Okay. Now I need to do continuity correction to get this into the normal distribution. Okay. Again, draw yourself a number line. Okay. Okay. This is less than or equal to 15. We need to make the set larger. We need to make that line longer. So take it up to the values that still round down to 15, which would be 15.5. So taking this into normal distribution, we would have the probability that x is less than or equal to 15.5. And this is in normal distribution. Okay, so right now we have the probability that x is less than or equal to 15.5 in normal distribution. Remember, whenever you do this, the thing that people always forget, always get it in terms of a less than or equal to or a greater than or equal to. If you have a strict inequality like we did at the top with x is less than 16, don't try continuity correction up there. Always get it into a less than or equal to or a greater than or equal to before you apply continuity correction. So we know that we have the probability that x is less than or equal to 15.5. We have a mean of 14.8 and a standard deviation of 3.6497. Okay. So I've got a mean that isn't 0 and a standard deviation that isn't 1. So what I would like to do is go from normal into standard normal. Okay. So I'm in normal right now. But because I don't actually have a lower bound in here, okay, I've got an upper bound of 15.5. I have no lower bound, and I'm not in standard normal, so I can't use -10 here, okay? In order to do that, I need to do a z transformation and get this into standard normal. So if I do x minus the mean divided by the standard deviation, okay, do that to both sides, I'm going to get 15.5 minus the mean of 14.8, divided by the standard deviation. Okay, if we quickly plug that into a calculator, so you're going to get 15.5 minus 14.8, and then divide that by 3.6497. You should get, this is equal to the probability that z, remember that this value here is now z, we've done a z transformation, is less than or equal to 0.1918. Okay. Now if we work that out, okay, we go into our calculator, okay, go to second and distribution and normal CDF, okay. Our lower bound, now that we are in standard normal, okay, so we've gone from binomial, okay, we've changed it so that we are still in binomial, but this time we have gone to a less than or equal to, okay, which you always need before you use continuity correction. You've then used continuity correction to get it into normal distribution. Then we have done a z transformation to get it into standard normal distribution. Now I am here. My upper bound will be 0.1918. My lower bound that I can use is -10. So my lower bound is -10. My upper bound is 0.1918. My mean is now 0 and my standard deviation is 1, because going from the normal into the standard normal, all I have done is pulled it back to give it a mean of 0 and a standard deviation of 1. So if we figure that out, click enter, we get, this is equal to 0.5761. Okay. What I could also do, just while you're on your calculators, if you actually go down to binomial CDF, okay, we now have the technology to use binomial CDF. This was used before they had the technology to do this, okay? But if you go right back up to the top of this problem, okay, you had the probability that x was less than 16, which was the same thing as saying that it's the probability that x is less than or equal to 15. Now remember, when you use binomial CDF, okay, it asks for the number of trials, which in this case is 148. It asks for the probability of success, that p-value, which is 0.1, and it asks for an x value. Remember, in binomial CDF, whenever you type in an x value, it's always the value that you have, in this case, where you have a less than or equal to that x value, okay? Whenever you use binomial CDF, make sure you've got it into terms of a less than or equal to. If you've got a less than or a greater than or a greater than or equal to, you have to flip it so that you have a less than or equal to. And whatever value it's less than or equal to is your x value for your calculator. So in this case, your x value is 15. So in your binomial CDF, you should have 148 trials, p is 0.1, and the x value is 15. If you go ahead and figure that out, you should get 0.5898 roughly. Okay, that's rounded. That is incredibly close. You're about 1/100th out from what we did from our approximation here. So your approximation gave you 0.5761. The actual answer using binomial CDF, which we now have, is 0.5898. Okay, you are incredibly close. If we hadn't have done that continuity correction, you can try this out for yourself. If we would have gone straight in and plugged into our normal distribution, if we hadn't done this adding 0.5, if we would have just plugged in 15 and done it that way, you would actually be further off from the answer. Okay, so what continuity correction does is it brings your actual answer, your approximation answer, closer to that actual answer. So make sure that you do that continuity correction when you go from binomial to normal CDF, or from binomial to normal distribution. Okay, and then you can use normal CDF in your calculator to use it. As I said, we now have calculators that can use binomial CDF. This is not used anymore, but what I want you to see is how they used to do this. Okay, so you will only really come across this in this chapter, but it is a useful thing to know, because this is how they used to have to do binomial distributions and do calculations in binomial distributions before they had the luxury of using binomial CDF, because they knew way more about normal distribution than they did about binomial distribution. So they just did all of their calculations in normal distribution and then said, okay, well, we're going to use that calculation to approximate the binomial distribution that we don't know that much about.